All right, so two last problems here to wrap up what we have in this lecture here. The first is a molecular scenes problem. So I'll set up the problem for you and we'll have you think about it. So again, the following scenes represent a phase change for water. So each of these represents a water molecule. So see if you can think about and name the phase change that's going on, and then think about the signs of enthalpy and entropy for this process, and then predict which of those four situations we're going to have. Is it always spontaneous, never spontaneous, or spontaneous at either low or high temperatures? So go ahead and pause the video and see if you might be able to walk through this thought exercise, thinking about enthalpy, entropy, and free energy. All right, so hopefully everybody's good recognizing that this is a condensation reaction. We're taking water that was in a gas phase and having it solidify, or I shouldn't say solidify, condense into a liquid phase. What might not be obvious to see is that this is going to be an exothermic process. Heat is released. If you're ever confused about a process, see about moving it in the reverse direction. If I had liquid water and I wanted to make it into gaseous water, yep, heat would have to be over on this side. Okay, so this is an exothermic process. We actually need to remove heat and energy from our system in order to get those gaseous water molecules to condense into the liquid phase. So because we know that it's an exothermic process, we know that delta H is negative. That's a winning situation. So if we think about what happens for entropy, entropy here is going to be unfavorable. We have gaseous water that's being forced to sit still as a liquid. So in our whole more molecules moving more philosophy, these molecules are moving less. So that's unfavorable from an entropy standpoint. Because we don't have a win-win or a lose-lose situation, we can cross off these two pieces. It's not going to be spontaneous at any temperature, and it's not going to be spontaneous at no temperature. So now we have to think about which of the temperature situations is going to be more favorable. All right, so because we know that entropy is unfavorable, we want to diminish its contributions, which means we diminish the temperature. We lower the temperature. All right, so we went through this problem just using the math and the equations to think about it, but you can actually walk through this problem logically. Think about this. If you wanted to have, let's say, water vapor in the air condense on a glass, would you want that glass to be a cold glass of iced tea or a hot cup of coffee? Obviously, an iced tea is going to condense more water on its outside than you would with a hot cup of coffee. So again, just another example of kind of putting a real example into place here. All right, last problem that we have here. Again, just showing us a chemical reaction. We don't really need to understand the context for what's going on, but they give us some pieces of information here. They actually give us free energy, enthalpy, and entropy for this process. So the questions ask us, is it spontaneous? How will delta G change if we were to increase the temperature? And if we assume that enthalpy and entropy are constant with temperature, that means that there's actually not a phase change that's occurring in this process. Is the reaction spontaneous if we heat it all the way up to 900? So try pausing the video and seeing if you could work through the answers to these questions. All right, A is pretty straightforward. If you want to answer the question, is a reaction spontaneous, you just need to look at the sign of delta G. Sign of delta G is negative, so that reaction is spontaneous. If we want to think about the temperature dependence of delta G, we need to look at the entropy. In this case, the entropy is a losing parameter in this system. So if we increase the temperature, that actually makes that losing contribution be more significant. So delta G will actually become more and more positive, becoming less and less spontaneous. So the last piece actually has us use our gold standard Gibbs free energy equation. And since delta H and delta S are going to be constant with temperature, we can put these same two values in, and we can just change the temperature, making sure we change it to Kelvin. So again, here's our delta H parameter. Here's our delta S parameter converted to kilojoules here. And then we need to convert our temperature to Kelvin to make sure to cancel out the units of Kelvin there. We see that delta G now becomes positive 22 kilojoules. Makes sense. We knew that as we increase the temperature, delta G would go from a negative number to becoming more and more positive until it eventually became 22 kilojoules at 900 degrees C. So one of the things that we'll move on to in our next lecture is just to say, well, okay, as we increase temperature, this became more and more positive until eventually it became 0. And then it continued to increase. So at 900 degrees C, it became 22. Well, at what temperature did it actually make that change? We're going to call that temperature the pivot point, and we'll learn in our next lecture how we actually solve for the answer for that question.